So now I get to tell you about the very cool randomized contraction algorithm for computing the minimum cut of a graph. Let's just recall what the minimum cut problem is. We're given as input an undirected graph, and parallel edges are allowed. In fact, they will arise naturally throughout the course of the algorithm. That is, for a given pair of vertices, we allow multiple edges to have that pair as endpoints. Now, I do sort of assume you've watched the other video on how graphs are actually represented, although that's not going to play a major role in the description of this particular algorithm. And again, the goal is to compute the cut. So a cut is a partition of the graph vertices into two groups, A and B. The number of edges crossing the cut is simply those that have one endpoint on each side. And amongst all of the exponentially possible cuts, we want to identify one that has the fewest number of crossing edges, or a min cut. So here's the random contraction algorithm. So this algorithm was devised by David Karger back when he was an early PhD student here at Stanford, and this was in the early 90s. So like I said, quote unquote, only about 20 years ago. And the basic idea is to use random sampling. Now, we've known forever, right, ever since quicksort, that random sampling could be a good idea in certain contexts, in particular when doing sorting and searching. And one of the things that was such a breakthrough about Karger's contraction algorithm is it showed that random sampling could be extremely effective for fundamental graph problems. So here's how it works. We're just going to have one main loop. Each iteration of this while loop is going to decrease the number of vertices in the graph by 1, and we're going to terminate when we get down to just 2 vertices remaining. Now, in a given iteration, here's the random sampling. Amongst all of the edges that remain in the graph to this point, we're going to choose one of those edges uniformly at random. Each edge is equally likely. Once you've chosen an edge, that's when we do the contraction. So we take the two endpoints of the edge, call them the vertex u and the vertex v, and we fuse them into a single vertex that represents both of them. This may become more clear when I go through a couple examples on the next couple of slides. This merging may create parallel edges, even if you didn't have them before. That's okay, we're going to leave the parallel edges, and it may create a self-loop edge where now both of the endpoints is the same. And self-loops are stupid, so we're just going to delete them as they arise. Each iteration decreases the number of vertices that remain. We start with n vertices, we end up with 2. So after n minus 2 iterations, that's when we stop, and at that point we return the cut represented by those 2 final vertices. You might well be wondering what I mean by the cut represented by the final 2 vertices, but I think that will become clear in the examples, which I'll proceed to now. So suppose the input graph is the following 4-node, 5-edge graph. There's a square plus 1 diagonal. So how would the contraction algorithm work on this graph? Well, of course, it's a randomized algorithm, so it could work in different ways. And so we're going to look at 2 different trajectories. In the first iteration, each of these 5 edges is equally likely. Each is chosen for contraction with 20% probability. For concreteness, let's say that the algorithm happens to choose this edge to contract, to fuse the 2 endpoints. After the fusion, these 2 vertices on the left have become 1. Whereas the 2 vertices on the right are still hanging around like they always were. So the edge between the 2 original vertices is unchanged. The contracted edge between the 2 vertices on the left has gotten sucked up, so that's gone. And so what remains are these 2 edges here, the edge on top and the diagonal. And those are now parallel edges between the fused node and the upper right node. And then I also shouldn't forget the bottom edge, which is edge from the lower right node to the supernode. So that's what we mean by taking a pair of vertices and contracting them. The edge that was previously connected to them vanishes, and then all the other edges just get pulled into the fusion. So that's the first iteration of Karger's algorithm, or one possible execution. So now we proceed to the second iteration of the contraction algorithm, and the same thing happens all over again. We pick an edge uniformly at random. Now there's only 4 edges that remain, each of which is equally likely to be chosen, so a 25% probability. For concreteness, let's say that in the second iteration we wind up choosing one of the 2 parallel edges, say this one here. So what happens? Well, now instead of 3 vertices we go down to 2. We have the original bottom right vertex that hasn't participated in any contractions at all, so that's as it was. And then we have the second vertex, which actually represents the fusion of all of the other 3 vertices. So 2 of them were fused, the leftmost vertices were fused in iteration 1, and now the upper right vertex got fused in with them to create this supernode representing 3 original vertices. So what happens to the 4 edges? Well, the contracted one disappears. That just gets sucked into the supernode and we never see it again. And then the other 3 go where they're supposed to go. So there's the edge that used to be the rightmost edge that has no hash mark. There's the edge with two hash marks that goes between the same two nodes that it did before. Just the super node is now an even bigger node representing three nodes. And then the edge which was parallel to the one that we contracted, the other one with a hash mark, becomes a self loop. And remember what the algorithm does is whenever self loops like this appear, they get deleted automatically. And now that we've done our n-2 iterations, we're down to just two nodes, we return the corresponding cut. By corresponding cut, what I mean is one group of the cut is the vertices that got fused into each other and wound up corresponding to the supernode. In this case, everything but the bottom right node. And then the other group is the original nodes corresponding to the other supernode in the contracted graphs, which in this case is just the bottom right node by itself. So the set A is going to be these three nodes here, which all got fused into each other, contracted into each other, and B is going to be this node over here, which never participated in any contractions at all. And what's cool is, you'll notice, this does in fact define a min cut. There are two edges crossing this cut. This one, the rightmost one, and the bottommost one. And I'll leave it for you to check that there is no cut in this graph with fewer than two crossing edges. So this is in fact a min cut. Of course, this is a randomized algorithm, and randomized algorithms can behave differently on different executions. So let's look at a second possible execution of the contraction algorithm on this exact same input. Let's even suppose the first iteration goes about in exactly the same way. So in particular, this leftmost edge is going to get chosen in the first iteration. But instead of choosing one of the two parallel edges, let's suppose that we choose the rightmost edge to contract in the second iteration. Totally possible, 25% chance that's going to happen. Now what happens after the contraction? Well, again, we're going to be left with two nodes, no surprise there. The contracted node gets sucked into oblivion and vanishes, but the other three edges, the ones with the hash marks, all stick around and become parallel edges between these two final nodes. This again corresponds to a cut, A and B, where A is the left two vertices and B is the right two vertices. Now, this cut, you'll notice, has three crossing edges. And we've already seen that there is a cut with two crossing edges. Therefore, this is not a min cut. So what have we learned? We've learned that the contraction algorithm sometimes identifies a min cut, and sometimes it does not. It depends on the random choices that it makes. It depends on which edges it chooses to randomly contract. So the obvious question is, is this a useful algorithm? So in particular, what is the probability that it gets the right answer? And we know it's bigger than 0, and we know it's less than 1. Is it close to 1 or is it close to 0? So we find ourselves in a familiar position. We have what seems like a quite sweet algorithm, this random contraction algorithm, and we don't really know if it's good or not. We don't really know how often it works, and we're going to need to do a little bit of math to answer that question. So in particular, we'll need some conditional probability. So for those of you who need a refresher, you either go to your favorite source or you can watch the probability review part 2 to get a refresher on conditional probability and independence. Once you have that in your mathematical toolbox, we'll be able to totally nail this question, get a very precise answer to exactly how frequently the contraction algorithm successfully computes the minimum cut.